Hey there, college algebra folks. I wanted to come back and do a couple of quick examples with you over a 4.5 material where we are looking at rational functions, right? And what we can see here in this particular example is I do give you the rational function f of x equals x squared minus 9 over the quantity x squared plus x plus 1. And if I write that so that you might be able to see that a little more clearly, here we have f of x equals the rational function x squared minus 9 over the quantity x squared plus x plus 1. Now, this is what we define as a rational function, if we remember. We have one polynomial function put over top of a second polynomial function in the form of this ratio, right? And that's where we come up with the understanding of this as a rational function, right? All this in the notes available on Blackboard. What we note, though, is we are asked in this particular case to determine the x and y-intercepts in the graph of this rational function. So if we focus our attention there, if we consider the case for maybe first finding our y-intercepts, right? Remember, our y-intercepts occur at x. Well, I should say occur at values of y where x equals 0, right? We might say here these are at y when x is equal to the value of 0, right? It's going to be given by, right, f at 0. It's going to be given by plugging 0 into our function here. And if we did plug in 0 into our function, we would note we would end up with 0 squared minus 9 over 0 squared plus 0 plus 1. Simplifying, 0 squared minus 9 in the numerator produces negative 9 over 0 squared plus 0 plus 1 in the denominator produces plus 1. And in the end, this simplifies to negative 9 in value. So our y-intercept is at, right, at the coordinate 0, negative 9. That is the location of our y-intercept. Now, one thing you may notice is this is highlighted in the notes. Your y-intercept can actually be seen here as the ratio of the two terms, right, in the numerator and the denominator given by the constant values here, right? Here we have negative 9 over plus 1. Those two terms formed into a ratio do give us this location for our y-intercept, all right? As for x-intercepts, what we want to remember about x-intercepts, right? They're at x when y equals 0, or when f of x is equal to the value of 0, right? Essentially, we want to solve f of x equal to x squared minus 9 over x squared plus x plus 1, all set equal to 0. And what we want to remember is, when does a rational quantity equal 0, right? Well, that is when the numerator equals 0 and when the denominator is not the value of 0. So to solve this out for 0, we are just going to take our numerator, x squared minus 9, and set it equal to 0. Now, solving that, we do have a quick way of solving that. We can add 9 to both sides, so that produces x squared equal to 9. And then to remove the square on the left-hand side, we can take the square root of the left. But if we take the square root of the left, we will have to take the plus or minus square root of the right. And that will lead me to saying that x must be equal to plus or minus the square root of 9, where plus or minus the square root of 9 is equal to plus or minus 3 in value. All right. One thing we would be able to check is that if we went back to our denominator and tried to substitute in +3 or -3, that certainly would not be equal to 0. So these would be our values of x, right? These are going to occur at x, where the output of our function f of x equals 0. We might say these are at the coordinates plus or minus 3, 0. Those would be our x-intercepts in this case. All right, so that is finding your x and y-intercepts, folks, with a rational function. For y-intercepts, you just substitute in 0, and you would be left with this ratio of the constant terms. Right? Whereas for x-intercepts, you do want to look at where your numerator equals 0. Setting where your numerator equals 0, right? And solving for that value of x will lead you to your x-intercepts. Now, I would always double check that these values of x do not make your denominator 0, right? But most cases, if this is in lowest terms or you've canceled all the common factors, you will encounter values of x where that would be the case, where x will not cause your denominator typically to equal 0. Right? But that is solving, right? Solving rational functions and working with evaluating them, folks. As I've always mentioned at the start of the semester, there are a couple of key skills. The evaluation we see here in the y-intercept process, where we can evaluate the function at a particular number. And then down here in finding our x-intercepts, it is a solving process. So take note, right? This is the case for an evaluate, and this is the case for a solve. All right? So, folks, that is our first example. I'll be back with another quick one. Hey there, college algebra folks, back with another quick example looking at the study of rational functions here, where in the next few problems we're going to be asked to determine or describe the end behavior of the rational function. All right, here's our first case here, and in case you can't see that, I'll write it a little bigger. This is the case for when we have the rational function f of x equals the ratio of x plus 3 to the quantity x squared minus 3x minus 10. All right. Now, if you've looked at the notes online presented in Blackboard, the study of end behavior, or the case for end behavior when looking at a rational function, does involve analyzing the degree of the polynomial in the numerator and comparing it to the degree of the polynomial found in our denominator. All right. If we take note to the polynomial found here in our numerator, that is the polynomial x plus 3, it has a degree of 1. What we say up here is we call that, I believe, the degree of n equal to 1. Whereas here in our denominator, it might be said to have a degree of m equal to 2. Right? It is a quadratic we see down there. It has a degree of m equal to 2. And if we're told back in the notes, if n is less than m, the rational function, right, has end behavior described by the horizontal line that line being the line y equals 0, which is also the x-axis in this case, folks, right? Or in any case when y equals 0 that you are dealing with the x-axis. In any case where your degree of the numerator is less than here your degree of the denominator, right, you are going to have end behavior described by the line y equals 0 or the x-axis, which means when I go to graph this, and I think about its graph, in the xy coordinate plane, the graph is going to end right along this line described by the x-axis. The left end is going to end here right on top of the x-axis, and the right end is going to end right on top of the x-axis. And as we've seen in our study of polynomials, knowing where the graph is ending, right, is extremely helpful information. And in the case where your degree of the numerator is less than the degree of the denominator, it will always end here on our x-axis. All right, so that is our first example. That is the example for x plus 3 over x squared minus 3x minus 10. If we look at another example, we might look at this example for case B here. All right, if we look at case B, we have the rational function f of x equals 5x squared minus 6x plus 1 over the quantity 3x squared plus 2x plus 2. That is a rational function. All right, and as the directions say, we are being asked to describe the end behavior of this rational function. And as the notes indicate, it does involve analyzing the degree of the numerator and denominator. Looking at the polynomial in the numerator and determining its degree, we call that the value of n. And looking at the polynomial found here in the denominator and determining its degree, we call that the value of m, and comparing those two values. Now in this case, we can see both polynomials found in the numerator and denominator have the same degree, both of those degrees being the value of 2. Right? And what we're told is if n equals m, end behavior is described by the horizontal line. It's again another horizontal line. Where in this case, we look at the horizontal line y equals, and it is the ratio of these leading terms compared to one another. More specifically, the ratio of the constants. We say it's a sub n over a b sub m. It is the value of 5. It is equal to the value of 5 over 3 in this case. All right. The end behavior, when the degree of the numerator over the degree of the denominator are the same, are given by these leading coefficients, right? The ratio found in our leading coefficients. And if you haven't noticed yet, in the analysis of end behavior, we are focused in on the first terms, the leading terms of the two polynomials found in our numerator and denominator. And in this particular case, when the degree of the polynomial in the numerator and the degree of the polynomial in the denominator are the same, if n equals m, you're again going to have more end behavior described by this horizontal line. And remember, what this is describing is a line in our coordinate system. Here I'm going to just draw the upper portion of this coordinate system, quadrants 1 and 2 here, where at the location of 5/3 along that y-axis, we might think of there being this horizontal asymptote, right? Where the left end of this graph is going to end on top of that horizontal asymptote on the left side, and the right end of this graph is going to end on the horizontal asymptote seen here on the right-hand side. Right? This is what we see occurring for the case when n equals m. You will encounter another end behavior description that is described by a horizontal line or this horizontal asymptote, but it's no longer at the origin. It actually moves to the position given by the ratio here of these leading coefficients. All right, so those are the first two examples I have here for end behavior. I'll be back in another quick video to go through the other two examples. Hey there, college algebra folks. A few more examples here looking at describing end behavior in rational functions. If we notice our third case here, for this function we see in case C, here we have f of x equals x cubed minus 5x squared plus 2x plus 1, all divided by x squared minus 6x plus 2. All right, where again our analysis is going to focus its attention on these leading terms in the polynomials found in the numerator and denominator of this rational function, right? And again, it's going to go back to comparing the degree of the numerator and denominator. In this case, the degree of the numerator is the value of 3, and the degree of the denominator, m, is the value of 2. Notice the numerator's degree is 3, the denominator's degree is 2. Remember, the degree of a polynomial is its largest exponent seen on our terms involving x. It's the largest power of x. All right. Now, in this case, we can see that when we compare n to m, n is certainly bigger than m. But more so, what we notice is that n is equal to m plus 1 in value. Excuse me. If you notice, or I should say, in the case of the degree of the numerator being 1 more than the degree of the denominator, right? If n equals m plus 1, all right, the end behavior, right, is described by what we call an oblique asymptote. All right, given by the what we call quotient of this rational function, which does mean that what I'm going to have to do is set up a division problem in this case. And unfortunately, most likely it's going to be a polynomial long division problem. So we have seen these. These were presented back in section 4.3. We looked at some polynomial long division. The last example of, or last video where I put up some examples, we started off with some polynomial long division. So in this problem, we're going to also have to do a little polynomial long division. All right, when it's the case that your degree of the numerator is 1 more than the degree of the denominator, and you're interested in end behavior, you are going to have to set this up. Where I will tell you, folks, you're not going to have to carry this out too far, though, because what you're interested in is just what's going to appear right here, right? Which is going to be the linear description of our quotient. Right? So it all starts by asking ourselves what times x squared gives us x cubed, and that is the value of x, where x times x squared is x cubed, x times negative 6x is negative 6x squared, and x times positive 2 is plus 2x. Where I'm now going to subtract this result from above, so x cubed minus x cubed is 0. Negative 5x squared minus negative 6 is actually plus 6x squared, so that would be plus an x squared would be left. And then 2x minus 2x is plus 0x's. And then we'll bring down the plus 1. We really don't need it because we're one step away from being done, we ask ourselves, what now times x squared gives us x squared? And that is the value of plus 1. Now that is it, folks. This is what I want. This quotient can be formed into the line, y equals x plus 1. Right? Where this line, y equals x plus 1, describes the oblique asymptote in this case. Right? If we think about the end behavior of this graph, right? The end behavior of this graph, if I fold this up so we can kind of see what's going on here, right? The end behavior of this graph is described by this, diagonal line we say, right? This diagonal line has a y-intercept of 1 and a slope of 1. So that means it's going to run 1 and rise 1, right, as we move from right to left to right in this graph, right? If we think about this asymptote, it is described by this oblique line, or what we might think of as this diagonal line, right? And what this tells us is the left end of my graph is going to end down here, pointing down on top of this diagonal line, and the right end of my graph is going to end here, pointing up on top of, again, this diagonal line. All right, and these two ends of this oblique asymptote are going to describe the end behavior seen in my rational function, right? So again, that goes back to the case where n, the degree of the numerator, is 1 more than the degree of the denominator. You are going to have to set up this polynomial long division, where I will tell you, folks, when it is the case where n is 1 more than m, you don't have to do a really heavy long division. You don't have to carry it all the way out to the end. You just have to really do it for 2 steps to obtain this linear description. Once you have that linear description, right, that line describes where your ends will be, where the ends of your graph will be in this rational function. All right, let's go through one more quick example here while we have it in front of us. All right, and this is actually another quick scenario, and that is looking at the end behavior here in this case. Here we have f of x equals the rational function x to the 4th plus 6x squared minus 2x plus 3 over the polynomial negative 2x squared plus 7x plus 1. Where again, the entire analysis does focus in on, right, the leading coefficients, all right, or more specifically, I should say the leading terms in this case. We are going to take note of the degree of the numerator and denominator. Again, the degree of the numerator is 4 in this case, and the degree of the denominator is 2. And if it's now the case where n is bigger than 1 more than m, which is what we see here. N is 4, and that is bigger than 1 more than m being 2. 1 more than m being 2 is 3, and n is bigger than that. So that is this scenario. If this is the case, n behavior is described by, right, the ends of the polynomial given by y equals a sub n x to the nth over b sub m x to the nth. Where what is this polynomial? It is the ratio formed by these leading terms. It is x to the 4th divided by negative 2x squared. Where if I do a little simplification here, with factors in the numerator canceling with factors in the denominator, this becomes negative 1/2 x squared. where we can note the function, right, or the equation y equals negative 1/2 x squared. This equation, right, note y equals negative 1/2 x squared has ends both pointing down, right? If we think about the ends of this, both ends are going to point down in this polynomial. So, in terms of our rational functions graph, really all we know in the case of the rational function here is that the ends of its graph are also going to both point down, right? They aren't going to follow any particular line, right? But the left half and the right half will both point down. And again, this goes back to our understanding of this polynomial behavior, right? Where that was all laid out in that table, folks. Remember that 2 by 2 table we had discussed in class, where if a sub n was greater than 0 or a sub n was less than 0, we saw two cases of results, or when n was even or n was odd, right? That also had some effect on our cases for results. And I really should say we have 4 results overall. If a sub n was greater than 0 and n was even, both ends pointed up. If a sub n was less than 0 and n was odd or even, both ends pointed down. And that is the case we see here. Our a sub n is negative 1/2, that is less than 0. And our value of the power here, which we think of as being n, is now even. All right? Remember, if a sub n was greater than 0 and n was odd, the left end would point down and the right end would point up. Whereas if a sub n was less than 0 and n was odd, the left end would point down and the left end would point up and the right end would point down. All right? So this is what I'm referring back to come up with this description here. Again, folks, this is the case for describing the end behavior where the degree of the numerator is greater than 1 more than the degree of the denominator, right? If your numerator is way bigger than the denominator in terms of degree, this is the approach we have for determining the end behavior. So here's another quick couple of examples, folks, where we have where we're studying the end behavior of a rational function. I'll be back with another few examples here in just a moment. Hey there, college algebra folks, back with another quick example in our study of rational functions, and that is the case of looking at what we call the vertical asymptotes in our graph, right? And determining the location for vertical asymptotes in our graph, right? In this particular case, we are asked to find the vertical asymptotes of, in case you can't read that, f of x equals the rational function x squared plus 3x minus 18 over x squared minus 2x minus 8. Right? And in the notes, which are presented up on Blackboard, we are told that in the case of a rational function, the vertical asymptotes are a result of a domain concern or a domain issue. And in rational functions, we have domain issues caused by our denominator. Our denominator is not allowed to equal the value of 0. All right? So to determine the locations for our vertical asymptotes, right, what we do with our denominator is we set it equal to 0, right? Vertical asymptotes, right, occur at x, where this particular case, x squared minus 2x minus 8 is equal to the value of 0. All right? You're always going to want to consider where your denominator equals 0. That will tell you where you have your x-intercepts. Oh, careful there, your vertical asymptotes. And the reason I'm mixing that up with X-intercepts is because remember, your numerator is where you find your X-intercepts. Wherever they equal 0, this is your X-intercepts. Whereas down here in your denominator where they don't equal 0 is where you're going to have your vertical asymptotes. So to find those, we set it equal to 0, that denominator, and solve. Now in this particular case, it is quadratic, so we might attempt to factor. And I do believe this one factors nicely, right? It factors into x and an x, and then I believe -4 and +2 work as our factoring. So x minus 4 times x plus 2 is equal to 0, and that does factor as such, where now we apply the zero product property. We take x minus 4, set it equal to 0. We take x plus 2, set it equal to 0, and solve those for x. We find x equals 4 or x equals -2. And what these values of x become, folks, right? These values of x are our locations for the vertical asymptotes, right? Our vertical asymptotes in this case are occurring at the values of x equal to 4 or the value of x equal to -2. In our graph, right? In our graph, at these locations, if I just fold this up so you can see the entire graph, at the location of -2 along the horizontal axis at x equal to -2, there is this what we call vertical asymptote in the graph. And at the location of 4 in this graph for values of x, there is this what we call vertical asymptote in our graph. And what a vertical asymptote is, recall, is as the graph approaches this asymptote, it's either going to go up it towards positive infinity or it's going to turn down it towards negative infinity. And that happens as it approaches from both the left or from values on the right. Between these asymptotes, the graph is either going to go up on this side and come down over here, or maybe it forms this U shape heading to positive infinity as it approaches both, or maybe this upside down U shape, or maybe even it starts down here and then heads up over here, right? That's all dictated by potential behavior between these vertical asymptotes. Out here, as the graph approaches from the right, it's either going to head up or it's going to head down. All right, so that's looking at the vertical asymptotes in a rational function. You do want to consider where your denominator cannot be 0, right, where you're going to have your domain concerns. Here we cannot be 4 or -2, so at those locations we will encounter some vertical asymptotes. All right, folks, just another quick example here in our study of rational functions. I think I have a couple of cases where we're going to come back and look at graphing this, putting it all together and coming up with a graphical picture. As we had noted back in class that in the process of functional analysis, obtaining the graph is our goal. And we'll be able to use all this and put it all together to produce a rather accurate sketch of the graph for a rational function. So we'll be back shortly to do a couple of examples of graphing. See you then. All right, college algebra folks, just last two quick examples here in our study of rational functions where we are looking at sketching out the graphs of a rational function. And I'll go ahead and bring my graph paper up here. We're in this first case, right? We are considering the sketch of this rational function where, again, there's going to be these little pieces of the analysis that we can start to put together. For instance, we should be able to find the y-intercept. We should be able to find the x-intercept. We should take note a little bit about horizontal asymptotes so that we can describe end behavior. And we might concern ourselves with some vertical asymptotes in this graph. Now, if you remember with respect to these parts, your y-intercept comes from the ratio of the constants found in your rational function. So in this particular case, our ratio is 8 over -4, right? Here for our y-intercepts, if we were to substitute 0 into this function, we would be left with the quantity -2 in value. So our y-intercept is at 0, -2. We might say that's right there, right, along our y-axis. As for x-intercepts, remember that occurs where your numerator equals 0. If we think about -3x plus 8 equaling 0, right, well, that's when -3x equals -8, or when x equals 8/3. Now, 8/3 is what? 2 2/3. So our x-intercept might be right there on our graph, right, at 8/3 in value. As for our horizontal asymptotes, remember we look at the degree of the numerator and the degree of the denominator here. And what we note about our horizontal asymptotes, if we just spend our moment there, n is equal to 1, m is equal to 1. So our horizontal asymptote is given by the ratio of these leading terms. Again, we go back to the ratio of the coefficients in the leading terms. That's going to be -3 over 1, right? -3 in the numerator, 1 in the denominator. So our horizontal asymptote is described by this line y equals -3. That is this line right here, right, where y equals -3 in value. The left end of my graph will end over here, the right end will end right there. And then the last bit gets into vertical asymptotes. And in the case for vertical asymptotes, remember we're looking at when does the denominator equal 0. Again, our denominator here was x minus 4. So when does x minus 4 equal 0? Well, that's when x equals 4. Right? So here's our value of 4. This graph would have a vertical asymptote described by this value. Now, in terms of putting it all together to graph, we would start over here on the far left. We would head to the right, passing through this x-axis, this y-intercept, passing through this x-intercept, and then very likely, in terms of how we're behaving along this vertical asymptote, we are heading up that vertical asymptote towards positive infinity, right? How do I know I'm heading up? Is that likely I'm crossing through the x-axis right here at this location, and there's not another x-intercept between here and this vertical asymptote. All right? In terms of the right half of my graph, I am starting over here on the right, where I had said my horizontal asymptote indicates end behavior. And as I move towards this vertical asymptote, I can either go up or down it. And chances are I am turning downward, right? Running down this vertical asymptote towards negative infinity. Now, how do I know it's likely doing that? Is because if I turned upward, I would have inevitably have an x-intercept, and I don't, right? I don't have an x-intercept out here. So using a little bit of inductive reasoning, or deductive reasoning, I can conclude I must be turning down. Now, don't forget you also have your calculator, folks. With these rational functions and sketching out their graphs, I would always double check your answers on the calculator. And when putting it into your calculator, take note you would want to organize your numerators and denominators into sets of parentheses here, just to keep them separate. So I do use a couple of parentheses there, hit my graph. And there we go. We can certainly see the graph here behaving a lot like what I have sketched out in my picture. All right? So take note, folks. You can always sketch out your graph and even look at tabled values on here if you need to help you with plotting some points on your rational functions. But I will be back with one more quick example here in just a bit. Hey there, college algebra folks, back with one more example here where we're looking at sketching the graph of a rational function. And in this particular case, we are looking at this function f of x equals the ratio x minus 4 times x plus 3, all divided by the quantity x minus 2. Where in this particular case, what we notice is that the polynomial found in the numerator, right, has been factored. And to perhaps consider it in its unfactored form is going to give us some useful information. If we expand this factored form, we will get x squared minus 4x plus 3x would become minus x times negative 12. And all that is over this quantity in the denominator, x minus 2. All right? Both of those forms might be useful to us. All right? If we start with our y-intercept, perhaps, that is evaluating f at 0, or focusing our attention on these constants at the end of this unfactored form, which would yield us negative 12 over negative 2, or positive 6 in value. Our y-intercept is at 0, 6. As for our x-intercept, we do want to set this numerator equal to 0, and in fact, that would be actually easily done with this quantity x minus 4 times x plus 3. If I take that numerator, x minus 4 times x plus 3, and set that equal to 0, that is our quadratic already factored here. So we would apply a little zero product property and find x minus 4 would equal 0, or x plus 3 would equal 0, or x would equal 4, or x would equal negative 3 in value, which does give us our two x-intercepts, negative 3, 0, and 4, 0. All right. In terms of vertical asymptotes, we might say, if we were to look at the case for vertical asymptotes, that is going to come from when our denominator equals 0. Right? We'll note x minus 2 equals 0 when x equals 2. Right? So that is going to be our description of the vertical asymptote. And our horizontal asymptote is going to come from our understanding of this degree, or the comparing the degree of the numerator to the degree of the denominator here. And what we notice is in this unfactored form, the numerator is 2 in degree, the denominator is 1 in degree, and here n again equals m plus 1. So this is going to require us to do a little polynomial division. This is the case of an oblique asymptote. So here we're going to take x squared minus x minus 12, this quantity in the numerator, and divide that by x minus 2. And again, we go through and just say, well, what times x gives us x squared? That would be x. That is x squared minus 2x. Subtract that from above. You have 0. Negative x minus negative 2x is negative x plus 2x, which is just plus x minus 12. And then what times x gives us x? Well, that would be plus 1 here. And the equation y equals x plus 1 is going to describe our, not horizontal asymptote in this case. This is going to be the case for a diagonal asymptote. All right, this oblique asymptote. So if we put all this information together in the sketch of a graph, let me give myself a little bit of room here so you all can see this. All right. If I take my y-intercept, that's at 0, 6, 1, 2, 3, 4, 5, 6. That would be located right here. My x-intercepts would be at negative 3 and 4. 1, 2, 3 is negative 3 right here. 1, 2, 3, 4 is 4 right here. And then I do have my vertical asymptote at x equal to 2. That is right here. We're going to have our vertical asymptote. All right. And our diagonal asymptote, our oblique asymptote, is going to be again described by this line y equals x plus 1. So it is this line that runs diagonal through space with a y-intercept of 1 and a slope of 1. So if we put all this information together in terms of a graph, the diagonal asymptote tells me my left end is going to start down here pointing down. And as I move towards this vertical asymptote, I'm either going to go up or I'm going to go down it. And based upon the point's location, there's a good chance I'm going to be heading up that vertical asymptote a lot like this. Whereas on the right side of the graph is going to end over here on the right. And as it approaches this vertical asymptote from the right-hand side, it's either going to go up or it's going to go down that asymptote. And based upon that point's location right there, there's a pretty good chance that it's going to head down. All right? Now, just to double check ourselves, we will again go in underneath our menu here in our calculator and consider graphing this polynomial, this rational function. If we graph this rational function, this is again y equals x minus 4 times the quantity x plus 3, all divided by the quantity x minus 2. Oh, I should get my parentheses back in there. X minus 2. All right? Or when I hit graph now, I should see a graph very similar to what I have sketched out in space here. These key locations being here at 6 on our y-axis, negative 3 on our x-axis, 4 on our x-axis, and then this vertical asymptotic behavior for the case of x equal to 2. All right, folks. This was our last set of examples here looking at rational functions in our study of rational functions. And as I have illustrated, these examples kind of work us through the different steps involved with understanding their behavior overall, and to help us obtain these graphs of these function types. Right? So, hope that helped. Hope you're hanging in there. If you need any other help, make sure that you're checking in with me on Blackboard Collaborate, and I'm more than happy to help out there, folks, as you work through these next couple of sections. So I'll be back in another video or two here illustrating some more examples from the following section. So see y'all then.